Have you ever really stopped to think about it? That invisible force that keeps your feet planted firmly on the ground, that keeps the moon circling us every night and holds all the planets in their epic dance around the sun? Well, that's gravity. And it is, literally, the force that shapes our entire universe. So, let's dive in and pull back the curtain on how this fundamental force really works. So, where does our story begin? Well, the legend goes it starts with a pretty simple observation. It's 1666 and Isaac Newton is just sitting under a tree when an apple falls. But here's the thing. Where most people would just see, a falling apple, Newton saw a question. Why did it fall straight down? And that one little moment of curiosity, well, it sparked a revolution. It led him to realize that the very same force pulling that apple was also holding the entire cosmos together.
And this is where it gets really brilliant. Newton took this gigantic leap of imagination, connecting that little apple falling on Earth to the massive moon hanging up in the sky. I mean, how could the same force possibly be responsible for both?
To get this, we need to talk about something called centripetal force. Just imagine you're swinging a stone on a string, right? The string is constantly pulling that stone in towards your hand, and that pull is what forces it to go in a circle. If you suddenly let go of the string, the stone just flies off in a straight line. Well, the moon is kind of like that stone, and guess what the string is? It's Earth's gravity. It's that constant pull toward the center that keeps the moon locked in its orbit around us. This huge insight led Newton to come up with his universal law of gravitation, and that word, universal, that's the absolute key. He figured out that this isn't just an Earth thing or a moon thing. Every single object in the universe, from a tiny speck of dust to a giant star, pulls on every other object. Get this, you are gravitationally attracted to your screen right now, and it's attracted to you. Wild, right?
So how strong is this pull, really? Well, Newton gave us a formula to figure it out. Now don't worry, I know equations can look intimidating, but let's just break it down. F is the force, the strength of the pull. M and M are the masses of the two objects. Basically, the more stuff an object is made of, the stronger its pull. And D is the distance between them. Now here's the crucial part. It's distance squared. That just means the force gets way, way weaker, much faster, as things get farther apart.
And what's so incredible is that this one simple law explains so much. It's the force that literally binds us to the Earth and stops us from floating off into space. It governs the moon's path around us and all the planets' paths around the sun. It's even what causes the tides in our oceans, all thanks to the gravitational tug of the moon. It's like the master architect of our entire solar system.
Okay, so we've been way out in space. Let's bring this cosmic force right back home and see how it affects us personally. We're going to talk about mass, weight, and what it actually means to be in freefall.
First off, a really quick but important clarification. You'll sometimes hear scientists talk about big G and little g. So big G is that universal constant from the formula we just looked at. It's the same exact number everywhere in the universe. Little g, on the other hand, is the specific strength of gravity's acceleration right here on the surface of Earth, about 9.8 meters per second squared. And that number? It changes from planet to planet.
And that brings us to another classic mix-up, mass versus weight. They are not the same thing. Your mass is the amount of stuff you're made of. It's constant. It doesn't matter if you're on Earth, the moon, or floating in deep space. Your mass is the same. Your weight, though, that's the force of gravity pulling on all that stuff. And since gravity changes depending on where you are, your weight changes too.
And to really put that difference into perspective, let's take a quick trip to the moon. The force of gravity there is much, much weaker. So, while your mass would stay exactly the same, your weight would be just 1/6 of what it is here on Earth. You'd feel incredibly light.
So, what happens when you just let gravity take over completely? Well, that's what we call free fall. When an object is in free fall, just like that apple in Newton's story, gravity is the only force pulling it down. It's gravity in its purest, most direct form.
But of course, most things here on Earth aren't in free fall. They're pushing against surfaces, right? They're sitting on the ground or on a table. And this interaction between the force of an object's weight and the area it touches brings us to our next key concept. Pressure.
Pressure is really simple. It's just the amount of force you apply over a certain area. The key relationship to remember is right there in the formula. For the same amount of force, the smaller the area you apply it to, the greater the pressure.
So let's make this super practical. Why is it that a sharp knife can slice right through a tomato with almost no effort, but a blunt one just kind of squishes it?
Well, it's all about pressure.
You're pushing down with the same amount of force from your hand in both cases, but the sharp knife's edge is an incredibly tiny area. This concentrates all of that force, creating immense pressure, enough to actually slice through the tomato. The blunt knife just spreads that same force out over a wider area, so the pressure is too low to do anything.
Okay, so what about the opposite? Why do school bags have nice wide straps? And for that matter, why did camels evolve to have such broad feet for walking on sand?
It's the exact same principle, just used in reverse. A wide strap spreads the weight of all those heavy books over a much larger area of your shoulder. This reduces the pressure and makes it way more comfortable. And a camel's broad feet do the same thing. They spread its weight out over more sand, reducing the pressure so it doesn't sink in. Pretty clever, huh?
All right, so we've talked about gravity in space and forces on solid ground. For our final stop, let's look at what happens when an object is in a fluid, like water or even air. Let's figure out why things float.
See, when you put something in water, it's not just gravity pulling it down. The water itself actually pushes back up. This upward force is called buoyancy, or sometimes upthrust. It's the reason you feel so much lighter when you get into a swimming pool.
So how strong is this upward push? Well, the ancient Greek genius Archimedes figured it out centuries ago. His principle is simple. The buoyant force pushing up on an object is exactly equal to the weight of the fluid that the object pushes out of the way. So, the more water you displace, the stronger that upward push becomes.
And this single idea is fundamental to so much of our world. A gigantic steel ship can float because its huge hollow shape displaces an enormous amount of water, creating a buoyant force strong enough to hold up its own massive weight. Submarines can sink or rise by using ballast tanks to change their weight. And hot air balloons rise because the hot, less dense air inside them is lighter than the cooler air they're displacing. It's all Archimedes.
All right, one last question for you, and it's one you might have experienced yourself. Have you ever noticed that it's way easier to float in the ocean than it is in a freshwater lake or a river? Why is that?
The answer is all about density. Seawater is packed with dissolved salt, which makes it denser than freshwater. Because it's denser, a bucket of seawater actually weighs more than a bucket of freshwater. And according to Archimedes, that means it provides a stronger buoyant force for every bit of water you displace. It gives you an extra lift, making it easier to stay afloat. So you know, from the silent pull that holds entire galaxies together all the way down to the upward push that lets a massive ship sail the seas, our world is just this constant, incredible dance between gravity pulling down and other forces pushing back. And if life ever throws you down, well, just blame gravity and bounce right back up.